Okay, I think we can get started. Our next speaker is Guido.
Yes.
Who will be talking about the Fredholm Factorization method directly applied to generalized Wiener-Hopf equations.
Thank you. Thank you. So, this is a method that we are going to present for the first time in this meeting. And it's a really follow on the meeting of 5 years ago, because we are going to deal wedge scattering in arbitrary linear media, and to solve this kind of problems we need this new technique, new methodology to solve the problem. So let me show some background of our work. We started from electromagnetic wedge scattering in isotropic media, penetrable wedges, and this is our collections of methods and results that have been published in 2020 in Wiley books. And then we have extended our methodology of generalized Wiener-Hopf technique in more complex problems, mixing planar and angular regions, but always in isotropic media. So you can see staggered structure, substrate, half substrate, polygonal shape, wedges over layers, double wedges. And these are problems that have been extended. Then, as a result of this meeting, in 2021, we have published a paper that started to generalize further the generalized Wiener-Hopf equation, introducing arbitrary linear media with its complexity. And from this spectral functional equation derived in this paper, we get generalized Wiener-Hopf equations. And now we introduce the Fredholm Factorization method directly applied to generalized Wiener-Hopf equation. Because in this media, the complex planes are tricky, and they are more complex than a classical generalized Wiener-Hopf equation for isotropic media. And this methodology can be applied in electromagnetic for arbitrary linear media, but can be extended also to other problems for wedge scattering, for example, in elasticity. So motivation is that in one propagation constant problems, we have effective and consolidated spectral methods like Sommerfeld-Malus technique, Kontorovich-Leb, that our generalized Wiener-Hopf equations. And in one propagation constant problems, we can define a complex angular plane W and Sommerfeld integrals. And this is a very effective technique because we can handle easily the physical branch cut in the problem. In arbitrary linear media, we have more than one propagation constant, usually in electromagnetics, but also in other physics. With reference to electromagnetics, only in special cases of non-isotropic media, we can reduce the problem to sub-problems with one propagation constant. In this case, you can resort to the previous techniques and get very effective, very convergent solutions. But in general, the one propagation constant methods cannot be used in spectral domain as in EM arbitrary linear media, also because it's not possible to define a unique complex angular variable W, but at the same time, if you know our technique, generalized Wiener-Hopf technique, we used to apply as a unique spectral mapping to modify the generalized Wiener-Hopf technique to classical generalized Wiener-Hopf equation to classical Wiener-Hopf equation, and then apply some approximation like the Fredholm Factorization. So in multiple propagation constants problems, we cannot have a mapping. We propose now a revisited generalized Wiener-Hopf equations method capable to handle wedge scattering in arbitrary linear media based on this new tool. So this is the flow chart of classical solution of generalized Wiener-Hopf technique for isotropic problem, and then I show some differences and additions that we are using now for this more complex media. We start from a description with Bresler and Markov transverse equation theory for stratified media. We extend this to angular region. We observe the properties of differential operator. We use green functions to represent solution. we get spectral functional equation in terms of field components on the faces of the angular regions, and then by imposing boundary condition, we transform these to generalized Wiener-Hopf equations. Then in classical isotropic problem, we can use a mapping to modify the generalized Wiener-Hopf equation to classical Wiener-Hopf equation. We can use exact or approximate factorizations to get a spectral solution and then apply asymptotics. Now, what we modify here is that this kind of representation, integral representation, can be anticipated to the level of functional equation before imposing boundary condition. So this is it's one possibility. We can do this here. Get compact kernels and so on, or properties of freedom. And the other thing is that we apply a different kind of freedom factorization that does not resort to mapping, because in arbitrary linear media we don't have this kind of mapping. So we modify this technique. Now, let me show some basics. In Bresler-Marx transverse equation theory for stratified media in electromagnetics, you have this report of 1956 that represent the Maxwell equation with this operator and these constitutive relations. And the constitutive relations are of tensorial form, so all parameters are tensorial. We have the field components and the differential operator. Then, considering a stratification along y, we can represent these equations in terms of a transverse field component. It means if you have a stratification along y, you have a z and x component for electromagnetic field here, and then you have a differential operator here that has this structure with three matrices defined in terms of the constitutive relations. Or we can assume that invariance along z of the problem, so this kind of behavior. And now we apply also the Fourier transform along x axis, represented here. C notation, it's quite different from mathematics. We use this kind of notation in engineering. And you have a system of differential equation of this form, so we can analyze the M operator, studying eigenvalue, eigenvector, and the reciprocal vectors. And we can show that in this 4x4 operator, we have two eigenvalues that represent progressive waves, and two eigenvalues are regressive waves. And we can perform solution in terms of homogeneous, a particular solution in terms of Green's function of this problem. And this kind of methodology can be used for stratified media and in classical literature with also transmission line representation, but we want to extend to angular regions. So we have stratified angular regions. Here we represent the space divided into 4 angular regions characterized by an aperture angle gamma. We focus the attention on region 1, which is this one. And if we use oblique Cartesian coordinate here, and we use the equation written for stratified media, then we rephrase the problem in this oblique Cartesian coordinate, we get this kind of operator, or a differential equation, system of differential equation, where we have applied the Fourier transform along u or x is the same, and invariance along z directions, perpendicular to the slides. And psi y is the transverse field in these directions. And M, we discovered M has special properties because M is completely related to the M of stratified media. You see this a representation of the decomposition of M in 3 matrices are related to the M of the stratified region. There is a dependence of aperture angle gamma, but it's very similar. And if you analyze the eigenvalue, eigenvectors of this new M for the angular regions, you discover that there is a relationship between the eigenvalues of these angular regions and the stratified equivalent regions. These are eigenvalue of the stratified regions, so this is the relationship. And then you have another important properties, that the eigenvectors are the same. So this is very nice. Okay, now to represent functional equation, to get functional equation for the angular regions, we use a Laplace transform. This is because we can relate the boundary condition directly. So this is our definition of Laplace transform, and if we apply Laplace transform to the differential problem written before, we have this new differential equation with the source term now. The source terms are the boundary condition for phase A in region 1. Our reference is region 1 for now. So we have this differential equation that with the source term with boundary condition on phase A. Okay, so if we apply the Green function procedure, we have an homogeneous portion of solution and a particular solution here. These are reported in our Proceeding of Royal Society A paper of 2021. And if we impose asymptotic behavior at infinity, V equal to infinity means the radiation condition, and so we can eliminate some constants and some integral parts, and we get this. This is the solution for a particular observation, V equals 0. It means we are observing the solution on phase O. We call phase O this and phase A this. These are the two phases of our problem. So if we look inside this expression and we apply scalar products against the reciprocal vectors, two of the four equations are of this form. You see, for I equal 3 and 4, we get this. That is a combination of tangent field components on phase O in spectral domain in Laplace eta plane. And on the other side, we cancel out these and we have only the term that is defined here. You see, this is a kind of another Laplace transform, but is defined in terms of this term. So here we rephrase the same term, defining psi as A. It's again a Laplace transform, but it's a Laplace transform on these phase components, and the spectral variable is mi. Mi is defined here. You see, there is a relationship between this mi and eta plane. These are the longitudinal propagation constant in stratified media. So it's the root square of k minus k square minus eta square. Okay, and the aperture angle gamma. So these are the functional equations. You can see that you have a spectral field component tangent on phase O here in eta plane, and the other terms is a spectral field component along phase I in a different complex plane. That's why it's a generalized generalized equation, because the unknowns are divided in two different phases and in two different complex planes, but related together. So now here we rewrite the same equation, but we defined on phase A the tangent field component. Here is the complete definition in local Cartesian coordinate x, capital X, y, capital Y, or you can see the definition in terms of cylindrical coordinate. And this is the left side, so phase O and phase A. And since we are transforming the right-hand side in terms of tangent field components here, we derived through Maxwell equation these matrices related to constitutive parameters. You see all the constitutive parameters of tensorial form combined together in terms also of the aperture angle gamma. We can repeat the same procedure for region 2. This is useful often for wedge regions because we like to model wedges that are symmetric with respect to x-axis, and we can have similar equations. You can see the difference here is that we reuse t, but with an aperture angle pi minus gamma, also in M, because if you think about region 2 and you reuse some of the solutions, then you see that the equivalent region 1 is pi minus gamma instead of gamma. Okay, now there is something new. First of all, we have the the four spectral equations, four functional equations, generalized. And first of all, we see that we have always the spectra along phase O in terms of a Laplace transform eta. That is our privileged Laplace complex plane. So, but using symmetry, using rotations, and we can rephrase all these two problems, region 1, region 2, in one to each other, and we can see that region 1 can be seen as a region 2 rotated of an angle gamma, or equivalent in the opposite directions. Region 2 can be seen as, and this is useful because if we rotate, we make phase O becoming this, and phase A becoming this, and we use the x direction as the one to define eta plane. So we, in some sense, we double the equations, but we privilege the spectral domain for all field components along A, O, and in the other side O and B rotating. We have the equations for the field components in eta plane for both. This impact on the constitutive relations, so we have a rotation of the material. So this is a kind of write down the type of equations. You see that on the left side you have plus unknowns of field components on phase O here, phase O here, phase A here. This is a duplicate equation. Phase A here, and the other side you have the dependence on M, and then you have all these spectral quantities defined with A and B. To get a generalized Wiener-Hopf equation, we impose the boundary condition, and to simplify the problem here we use perfect electric boundary condition, so the tangent field components of E, Z, and E rho are cancelled. You get this kind of equations. And now there is the novelty. We cannot use any mapping because you see we have 4M. So 4M are combined together. So we use Cauchy decomposition here. We apply to represent this kind of unknown, the minus unknown in minus M, with this formula, the Cauchy. We extract some sources. For simplicity, we use that the plus unknown is non-standard with a pole on the upper half plane. And if we apply this formula to this equation, then we get the integral representation where the unknown, you see the unknown, are only in the eta plane, in eta plane. It's the only one that we use at this point, except for the source term, but that's not a problem. So now we go into the regularization, what we have done for freedom integral equation, usually in classical Wiener-Hopf equation. So we perform the smile contour on left side and the smile contour on the right side, and then we make some mathematical trick to get compact kernels here. And what we see, what we extract is also in this formulation is that we have an extra term, this term. So we have we need to evaluate this term clearly in exact mode. There are some closed form solutions that have some problem of convergence, but we can perform this integration also numerically along the branch cut in the lower half plane. You see an example of M. So it's in the upper half plane. So the formula is the application is correct for Cauchy decomposition formula. And these are the general kind of equations, left-hand side equal to right-hand side, that we are going to solve in as a freedom with the freedom, these new freedom applications. Okay, but here is an insight. Solving that equation, so we have the spectral components along the two phases. We are interested also in the spectral components on any directions, because we want asymptotics for every point in region 1. To do that, we have two solutions. One is by superposition, because if you go back to the first slide, you remember there is a portion of of homogeneous solution, a portion of particular solution. And you see that these terms for spectra along phase O, these are for sources like radiation sources from phase I, so the other terms are related to phase O. So you can use duplicate equations and reverse, and you get the spectrum on phase A, and with the homogeneous part that is related to phase E, and the other is related to phase O. These are the complex terms, the difficult terms to evaluate. But we can use superposition and use asymptotics on the homogeneous part only. Other solution is to split the angular regions and have a couple of system of equations for one subregion, the other subregion, and get the spectra along one directions. These are all methodology to get the field at the end. But now I want to show some validations. So first of all, I want to validate Fredholm Factorization method directly applied to generalized Wiener-Hopf equation. And we will do this in a very simple case because we want to show that the correctness of the method. And so we are going to analyze region 1 with perfect electric boundary conditions. And the second validation will be to show two particular problems in arbitrary linear media, in non-isotropic media. So I will show some results on gyrotropic media and in biaxial media. So this is the validation for the perfect electric conducting wedge region 1. I reported here the simplified expression for M in case of this isotropic region. So we have only one M in this case. So it could be applied the classical mapping to get classical Wiener-Hopf equation. We have the eigenvector. We apply the functional equations. These are the one on top, the first one. The second one are the duplicated ones. And these are reported in several of our papers. And we apply then boundary condition to get classical generalized Wiener-Hopf equation. Are very simple in this case because it's a perfect electric conducting wedge at normal incidence. We can separate the polarization in this case, but now I want to introduce the direct Fredholm factorization. So if we look to the equation, functional equation and its duplicated one, you have this system of equations. So you have the plus unknown here in eta, plus unknown here, it's like phase O, phase A, phase O, so they are interchanged. We apply the Cauchy decomposition formula, so we represented the M dependence in these terms. We apply the Smile contour and some trick for regularization here. And in the case of perfect electric conducting wedge, isotropic region 1, looking only to EZ polarization, you have this definition of all terms of the equations. And finally, you get this kind of equation. You see that there is a compact kernel here, some sources due to non-standard terms, and this ME is the operator shown before that we need to compute with high accuracy. So let's go to the discretization of our problem. We use just sample and hold, few sample, truncation of interval. Usually we use contour warping in the spectral domain, eta spectral. So we go in a diagonal, not in the real axis, to be a little bit far from branch cuts and branch points that we use to have a small imaginary part. And this is the formula for reconstructions here. In this case, in this example, we took an aperture angle of 0.7 pi, an HZ polarization with this intensity, this incident angle with respect to the x-axis. Theta is the contour warping, and here you see the convergence. We have the exact result. We know the exact result in closed form. In this case, is the black solid line is the one a little bit shifted from the others, and you see there is a small convergence on the other. There is a perfect convergence somewhere, but sometimes there is a weak convergence. You see also on this, this is the spectra, sorry, the spectra along minus k cosine w, because we are interested on this collocation of observation because of asymptotics later for GTD diffractions. And here you see the spectra for HZA on phase A. So also this is black solid line is the one a little bit shifted here, and you see the convergence going toward the solution, but some lack of convergence on the extreme. It means for W equal minus pi and 0, these are corresponding to K and minus K. The K is the physical branch cut, minus K in the unknown is an offending singularity for the approximation. Here you see the convergence in terms of relative error in log scale. Also, you can see that the extreme are not good, or of course are not good the relative error where you have the spectral equal to 0, but in the other rest of the portion is good. So here we have improved the solution by reinforcing the generalized Wiener-Hopf equation. This is the kind of generalized Wiener-Hopf equation we have, and we have a duplicated equation also. And so we use the spectra, approximate spectra here, and we get a iterated spectra in the other side. And if we look to the spectra now, in particular, we multiply also for sin W for GTD reason, you see that the black solid line, the exact, and the red line, the freedom integral equation directly with the iteration are very close to each other. Also at the end extreme of the interval, here you can see that the error is smoothed for these cases. And this is because that we take spectra far from branch cut, and the branch cut is correctly reconstructed by the kernel. And here you can see by using SDP and GTD diffraction coefficient, you can see that without this iteration you have the blue line, and instead the exact and the last results, black and red lines are overlap. Also the phase is more sensible to errors, and you can see the relative error now in red here, that is good. Now let me switch to some application of arbitrary linear media. This is a media, it's called the electric gyrotropic media. We have the evaluation of eigenvalues reported here in terms of two propagation constants. You can see the two propagation constants here. So there is some definition that comes from literature here for the different parameters. We have the eigenvectors, the definition of M. In this case, since we are analyzing coming from the literature, the half plane, we have the aperture gamma, the aperture angle gamma is pi. We have that M is equal eta. So it's, of course, it's simplified also in this case. These are the functional equation. You can see the decoupling of two polarization at normal incidence. We can repeat this for region 2. We can couple, summing and subtracting the equation. You can have EZ and HZ formulations here. And in particular, we can see that on EZ we have a behavior like isotropic media. That's common for gyrotropic media. And then here you can see that in the second equation of EZ you get the right kernel proposed in this paper of 1963 with a surface wave excitation, and solution can be derived in classical form or by this new methodology. And last results is about biaxial media. We start from equations that in this case are defined for angular regions, for a generic gamma. We get the eigenvalue of stratified. You know the relationship of eigenvalue with the angular regions. Here we have the M value. In this case, we have two M values. These are the functional equation for region 1. If we want the generalized Wiener-Hopf equation, we need to impose boundary conditions, and in this case are perfect conducting. Here are reported the equation for region 1, again for region 2 after boundary condition. And we focus the attentions on the decoupling of the two polarization. We focus the attention on EZ. These are the equation. We can sum and subtract, perform exact solution, exact factorization, or perform the numerical scheme. In this case, for the biaxial media at normal incidence with an half plane, we have m equal eta for the aperture angle gamma. And here you can see the numerical results for the far field at k rho equal 10, where in our asymptotic solution you can see the geometrical optics with shadow boundary. Then you can see the GTD diffraction, uniformized GTD diffraction coefficient, uniform theory diffraction coefficient in orange, and the total field is in green. And this is the finite element solution for this kind of problem, and you can see the match. And here, final conclusion, we have presented the theoretical package to face wedge scattering in arbitrary linear media. We have already a little bit studied a closed form solution for particular wedge problems, like in biaxial media and geotropic media, but we need to finalize this item. The theory is presented in this work, and also is going to be submitted to applied science in a special issue. And we will work on mathematical computation of fields in half-plane problems like the one I showed before. Here are the first results. And in particular, we will analyze wedge analysis with respect to half-plane, more complex, of course, but the theory here can establish the solution. And we will extend this analysis to other boundary conditions, and we are going to study also this application in other physics. Thank you.
So we're out of time, but if we want one quick question while we change speakers, that should be fine. So any quick questions? No? All right.
Okay. Thank you.